Most earthquakes don't announce themselves as important, but occasionally one moves just enough to suggest that what we felt on the surface is only a small expression of something much larger happening underneath. On the evening of April 13th, 2026, a magnitude 5.7 earthquake struck western Nevada, near a quiet stretch of desert not far from Silver Springs, a place that rarely enters national attention and even more rarely appears in conversations about seismic risk. The event itself was not extreme by global standards, but the way it behaved immediately set it apart from what seismologists would normally expect from an earthquake of that size. The rupture occurred at a shallow depth, estimated between 5 and 9 kilometers beneath the surface, a range that significantly alters how seismic energy is transmitted. When earthquakes originate this close to the surface, the waves have less material to pass through before reaching populated areas, which means less energy is lost along the way and more of it is felt directly as sharp, abrupt motion rather than a distant rolling sensation. Reports from nearby cities such as Reno and Carson City describe the shaking as sudden and forceful, not prolonged but intense enough to be unmistakable. What makes this event unusual is not simply the intensity close to the epicenter, but the distance over which the shaking was reported. People felt it far beyond the immediate region, across the Sierra Nevada and into California's Central Valley, including cities like Sacramento, Modesto, and Grass Valley. This is a span of hundreds of kilometers, crossing significant geological barriers that typically reduce the reach of seismic waves. For an earthquake of magnitude 5.7, this kind of footprint does not align cleanly with standard attenuation models, which predict a faster decay of energy with distance. At first glance, there are reasonable explanations for why an earthquake might be felt over a wide area. The crust in parts of the western United States can act as an efficient conduit for certain types of seismic waves, allowing them to travel farther than expected, especially when combined with a shallow source depth and favorable geological structures. However, the April 13th event sits just outside the range of what those explanations comfortably account for. It is not impossible, but it is noticeably uncommon. And in seismology, uncommon patterns often point to underlying structures that deserve closer examination. Initial data released by monitoring agencies confirm the basic parameters of the event: magnitude, depth, and location. But the broader pattern of shaking began to draw attention from those looking beyond the headline numbers. The distribution of felt reports suggested that the energy was not dispersing uniformly. Instead, it appeared to be traveling along preferred pathways through the crust, maintaining coherence over distances where it would typically dissipate. This kind of behavior is not random. It implies a structural influence, something about the geology of the region guiding and sustaining the motion. That observation leads to a more fundamental question, not about the earthquake itself, but about the system in which it occurred. Because earthquakes do not happen in isolation. They are expressions of stress release within a larger mechanical framework. And the characteristics of that framework determine how energy is stored, released, and transmitted. The April 13th earthquake did not simply occur in Nevada. It occurred within a specific tectonic environment whose properties are not widely recognized outside scientific circles. The anomaly, therefore, is not just that a moderate earthquake was widely felt, but that it behaved in a way consistent with a more complex and interconnected system beneath the surface. A system capable of transmitting energy efficiently across large distances and potentially redistributing stress in ways that are not immediately visible from a single event. This is where the focus begins to shift, away from the earthquake as an isolated incident and toward the structure that made its behavior possible. Because if a magnitude 5.7 can produce this kind of reach under the right conditions, then the question is not what this event was, but what the same system might produce under greater stress, and whether what happened on April 13th was simply a routine release of energy or an early indication of something still unfolding. That shift in focus leads directly to the system responsible for shaping both the behavior and the reach of this event. A system that does not appear on most public hazard maps in any meaningful way and is rarely named outside of academic literature. The region that ruptured on April 13th is part of what geologists call the Walker Lane, a broad zone of deformation running along the eastern edge of the Sierra Nevada, extending through western Nevada and into the Basin and Range province. Unlike the San Andreas Fault, which is often visualized as a single continuous line, the Walker Lane is not a single fault at all. It is a distributed network, a collection of intersecting and parallel fault strands, where the crust is being pulled apart and sheared at the same time. This distinction is not semantic. It fundamentally changes how the system behaves. A single major fault tends to accumulate strain along a relatively well-defined plane and releases that strain in more predictable rupture patterns. A distributed system like the Walker Lane spreads that strain across multiple structures, some mapped and some only partially understood, which allows stress to move laterally through the network rather than remaining confined to one location. In practical terms, this means that an earthquake in this region is less likely to be an isolated fracture and more likely to be part of a broader adjustment across several connected fault segments. The reason this system exists at all is tied to plate tectonics at a much larger scale. The motion between the Pacific Plate and the North American Plate is not fully accommodated by the San Andreas system alone. While the majority of that motion occurs along the California coast, a significant fraction, approximately 20 to 25%, is redirected inland into the Walker Lane. This is not an abstract estimate, but a measurement confirmed by geodetic data from GPS networks which track ground movement at millimeter precision over time. Stations across the large Nevada show consistent northwestward motion, indicating that the region is actively participating in the larger plate boundary process. That redistribution of motion creates a specific type of geological environment known as transtension, a combination of lateral sliding and crustal extension. In this setting, some faults move horizontally while others drop vertically, producing a fragmented architecture where blocks of crust shift in different directions simultaneously. The result is a landscape that appears quiet on the surface but is mechanically complex at depth, with stress accumulating in multiple orientations rather than along a single dominant plane. This complexity helps explain why the April 13th earthquake did not behave like a simple rupture. The energy released by the event did not radiate outward evenly in all directions. Instead, it appears to have interacted with the existing structural fabric of the Walker Lane, guiding seismic waves along certain differentials where the crust transmits energy more efficiently. One important mechanism involves regional surface waves, often referred to as LG waves, which can travel long distances within the crust when conditions allow. The basin and range geology, with its alternating layers of dense rock and sediment, creates a kind of natural waveguide, allowing these waves to maintain strength over greater distances than expected. At the same time, the shallow depth of the rupture increased the proportion of energy converted into surface waves rather than deeper body waves. Surface waves tend to persist longer and travel farther, especially when they encounter sedimentary basins like those in California's Central Valley, where softer materials can amplify motion. This combination, shallow source distributed fault network and efficient wave propagation pathways, produces a system where even moderate earthquakes can generate disproportionately large felt areas. But the implications extend beyond wave behavior into how the crust responds after the regions. Initial rupture. In a simple fault system, aftershocks typically cluster around the main rupture zone, forming a roughly symmetrical pattern as the surrounding rock adjusts. In the Walker Lane, the aftershock sequence following April 13th showed a different structure, elongated along a northeast to southwest trend, consistent with the orientation of known fault strands in the region. This suggests that the stress released by the main shock did not simply dissipate locally, but was transferred across multiple connected structures. This process, known as stress transfer, means that one rupture can alter the failure conditions of nearby faults, increasing or decreasing the likelihood that they will slip next. In a networked system, the effect is amplified because there are more pathways for that stress to move through. The crust behaves less like a single cracking surface and more like a web, where tension can shift from one strand to another. This does not guarantee that a larger event will follow, but it does mean that the consequences of any single earthquake are distributed across a wider system than the initial rupture might suggest. Understanding this framework changes how the April 13th event is interpreted. It is no longer just a magnitude 5.7 in western Nevada, but a localized expression of a much larger mechanical system, one that is actively accommodating plate motion and redistributing stress across a broad region. The question that follows is not limited to what happened during those few seconds of shaking, but how that energy has altered the system as a whole, and whether the adjustment that began on that night has fully played out or is still in progress. The pattern becomes clearer when you stop looking at April 13th as an isolated data point and start placing it against the longer timeline of the Walker Lane system. A timeline that does not read like a sequence of random events, but more like a fragmented record of a system that releases stress in uneven, sometimes clustered ways that only make sense in retrospect. In 1915, the Pleasant Valley earthquake ruptured a long stretch of fault with a magnitude estimated around 7.2, producing surface displacement that physically tore open the desert floor in a way that would be unthinkable in a modern urban setting. What matters is not just the size of that event, but its location inside the same broad deformation corridor that produced the April 13th earthquake, suggesting that the system has been capable of large energy releases for more than a century without any fundamental change in its behavior. 17 years later, in 1932, the Cedar Mountain earthquake delivered another magnitude 7 class rupture in central Nevada. Again, minimal infrastructure meant minimal attention. But from a geophysical perspective, the implication was clear. The Walker Lane was not producing rare anomalies. It was producing repeatable, large-scale ruptures across different segments of a distributed fault network. The spacing in time between 1915 and 1932 might suggest independence, but that assumption begins to break down when you examine what happens next. In 1954, the system behaved in a way that challenges the intuitive idea of earthquakes as isolated events. The Fairview Peak earthquake struck first, followed just minutes later by the Dixie Valley earthquake. Two separate magnitude 7 earthquakes, two different fault strands, one tightly coupled sequence. This is not coincidence in any meaningful physical sense. It is a demonstration of stress transfer in action, where the rupture of one fault changes the stress field enough to trigger failure on another nearby structure. The Walker lane in that moment revealed itself not as a collection of independent faults, but as an interconnected mechanical system capable of cascading failure. That historical pattern reframes the April 13th event in a subtle but important way. A magnitude 5.7 does not belong in the same category as those earlier magnitude 7 ruptures in terms of energy release. But it does belong to the same system, governed by the same stress field, operating under the same physical rules. The question is not whether April 13th matches those past events in scale. It clearly does not. But whether it fits into the same pattern of distributed strain release that occasionally organizes itself into larger system-wide responses. What complicates this picture further is the expansion of the affected footprint, not just in physical terms, but in human terms. In 1915, 1932, and even 1954, the Walker Lane ruptured beneath regions that were sparsely populated, with little infrastructure to amplify the consequences. Today, that is no longer the case. The Reno-Carson City corridor sits directly within this deformation zone, and the growth of this region over the past few decades has introduced a new variable into the system: exposure. The geology has not fundamentally changed, but the stakes have. This shift becomes even more significant when you consider how seismic waves propagate beyond the immediate rupture zone. The April 13th earthquake demonstrated that energy released within the Walker Lane does not remain confined to Nevada. It travels westward, interacts with the geological structures of the Sierra Nevada, and then enters the sediment-filled basins of California's Central Valley, where it can be amplified. Cities like Sacramento, Modesto, and Fresno, often conceptualized as distant from major fault systems like the San Andreas Fault, are not isolated from Walker Lane events in the way public perception might suggest. This creates a mismatch between perceived and actual risk. The Central Valley is typically framed as a lower hazard region because of its distance from coastal fault systems. Yet the April 13th event shows that distance alone is not a sufficient metric. The pathway that seismic energy takes, shaped by crustal structure and sedimentary amplification, can extend the reach of an earthquake far beyond what magnitude alone would imply. In effect, the Walker Lane expands its influence westward, not by moving, but by transmitting energy through a geological configuration that favors long-distance propagation. There is also a broader spatial implication that emerges when you map these events over time. The Walker Lane is not a single fault line, but a wide belt, roughly 100 kilometers across, containing multiple Sakriya strands that share the burden of accommodating plate motion. This distributed nature means that large earthquakes do not have to repeat on the same fault segment to maintain the system's overall strain budget. Instead, different parts of the system can activate at different times, creating a pattern that appears irregular locally but consistent when viewed at the scale of the entire deformation zone. This is where the concept of a felt footprint becomes important. The April 13th earthquake was experienced across a wide region not because it was unusually large, but because it occurred within a system that efficiently channels seismic energy across structural boundaries. That efficiency, combined with sediment amplification in downstream basins, effectively enlarges the functional size of the event. A moderate earthquake, under the right conditions, behaves like a much larger one in terms of its perceptual reach. And that leads to a more subtle consequence that often goes unaddressed. As population and infrastructure expand within and around the Walker Lane, the system's historical behavior intersects with modern vulnerability in ways that were previously irrelevant. Past earthquakes did not produce large-scale disasters, not because the system was less active, but because there was less to damage. The absence of historical catastrophe is not evidence of safety. It is evidence of past conditions that no longer exist. So the timeline from 1915 to 2026 does not describe a system becoming more active or more dangerous in a physical sense. It describes a system whose consistent behavior is increasingly intersecting with human systems that are less prepared for it. The earthquakes have not changed their nature. The context in which they occur has. And when you extend that trajectory forward, without assuming escalation, but without dismissing it either, you arrive at a position that is difficult to simplify. The Walker Lane does not need to produce a magnitude 7 earthquake tomorrow to matter. It only needs to continue doing what it has already demonstrated it can do. Releasing strain across a distributed network, occasionally synchronizing that release into larger events, and transmitting the resulting energy across a region that is more connected, more populated, and more dependent on infrastructure than at any point in its recorded history. Which raises a question that does not resolve cleanly, because it depends on variables that are still unfolding. Variables tied to how strain accumulates across mapped and unmapped faults, how stress redistributes after each event, and how a system like this decides, without warning and without pattern that we can fully decode, when a sequence remains local and when it becomes something larger. The present moment is defined less by what has already happened and more by how the system is adjusting in response to it. Because an earthquake is not a single event, but a redistribution of stress across a network that does not stop moving once the initial rupture ends. In the days following April 13th, the aftershock sequence began outlining the geometry of the fault system in a way that static maps never fully capture. Each small event marked a point where the crust was still responding, still settling into a new configuration of stress. The pattern was not random. It stretched along the same northeast to southwest trend that defines the Walker Lane, suggesting that multiple fault strands were participating in the adjustment. This is what a system looks like when it is rebalancing. Not isolated fractures, but a connected structure redistributing force across distance. The uncertainty lies in what that redistribution leads to next. Because the distinction between a system that is stabilizing and one that is preparing for another release is not immediately visible. Seismology approaches this problem statistically, estimating probabilities based on past sequences. But the limitation is fundamental. A magnitude 5.7 can be the main shock in one case and a precursor in another. And the physics that governs both outcomes is identical at the moment it happens. For events of this size in the western United States, historical data suggests that the probability of a larger follow-up event within weeks is low, but not negligible. In a system as structurally complex as the Walker Lane, that probability carries wider uncertainty than the baseline implies. This leads to a tension between statistical reassurance and structural reality. Most sequences decay. That is the expected pattern. But the Walker lane is not a simple fault where stress accumulates and releases along a single plane. It is a distributed system where stress can migrate, where one rupture can increase the likelihood of failure on adjacent strands. The 1954 sequence demonstrated that this transfer can occur rapidly under the right conditions. The question now is not whether such behavior is possible, but whether the current configuration of stress is moving in that direction or away from it. And that is a question that cannot be answered in real time with certainty. What makes this moment more consequential is not just the geophysics, but the social landscape that now sits on top of it. The Reno metropolitan area has expanded significantly in recent decades, transforming from a relatively small regional center into a growing hub with logistics infrastructure, technology investment, and population density that did not exist during earlier major earthquakes in the region. Nearby, Carson City functions as both a political center and a residential base, while corridors like Interstate 80 connect the region to broader national supply chains. These are not abstract points on a map. They are systems that depend on continuity, on infrastructure performing as expected under stress. The difficulty is that much of this built environment developed under an incomplete understanding of the underlying hazard. Unlike California, where repeated destructive earthquakes forced continuous updates to building codes and engineering practices, Nevada did not experience the same sequence of urban disasters. The absence of visible catastrophe delayed the institutional response. As a result, parts of the infrastructure within the Walker lane were designed to standards that did not fully account for the level of seismic risk that current data suggests. This creates a mismatch that is subtle but critical. A moderate earthquake like the April 13th event tests the system lightly and produces little visible failure, which can reinforce a perception of resilience. But that perception does not scale linearly with magnitude. The difference between a 5.7 and a 7.2 is not incremental. It represents a massive increase in released energy, and with it, a fundamentally different stress on buildings, bridges, and lifeline systems. The absence of damage at lower magnitudes does not guarantee performance at higher ones. It only confirms that the threshold has not yet been reached. At the same time, awareness of the hazard remains uneven. Many residents in this region have relocated from parts of California where earthquake preparedness is part of everyday life. Yet, the cultural infrastructure that supports that awareness does not fully transfer with them. Emergency planning, retrofitting, and risk communication operate at different levels of priority. The result is a population that is, in aggregate, less prepared than the geology would justify, living above a system that has not changed its behavior to match that gap. Looking forward, the deeper layer of the problem extends beyond immediate hazard into long-term tectonic evolution. The Walker lane is not simply an active fault zone. It is part of a broader goats and thuds that may be reshaping the boundary between the Pacific and North American plates. Current geodetic measurements indicate that a significant portion of plate motion is already being accommodated within this, rather than exclusively along the San Andreas Fault. This redistribution of motion is gradual, measured in millimeters per year. But over geological time, such rates accumulate into large-scale structural change. The implication is not that the Walker lane will suddenly replace the San Andreas in any immediate sense, but that the boundary between plates is not fixed. It evolves, it shifts, and when it does, the boards that were once considered secondary can become primary pathways for tectonic strain. From a hazard perspective, this means that the Walker lane is not a system in decline or stability. It is a system actively participating in the ongoing mechanics of plate motion, with no indication that its role is diminishing. This long-term perspective introduces a different kind of uncertainty. Not the short-term question of whether another earthquake will follow April 13th, but the broader question of how strain will be distributed across the western United States over decades and centuries. As populations continue to grow in regions like northern Nevada, and as infrastructure becomes more interconnected and more critical to national systems, the consequences of that distribution become more significant. And yet, there is a structural limitation in how well this can be understood. Many of the faults within the Walker lane remain incompletely mapped. Some are known only through indirect geophysical signals. Others have not been studied in sufficient detail to establish their history of past ruptures. This creates a situation where the overall strain rate is measurable, the total energy budget is constrained, but the specific pathways through which that energy will be released remain uncertain. It is a system where the balance sheet is known, but the individual transactions are not. The April 13th earthquake in this context serves as both a data point and a reminder. It provides new information about which parts of the system are active, how stress is being redistributed, and how seismic energy propagates through the region. But it also highlights the gaps that remain, the areas where the system is still not fully characterized, where future ruptures could occur on structures that have not yet been the focus of detailed study. So the present risk is not defined by a single probability or a single scenario. It exists at the intersection of a fault system, a growing and partially unprepared population, and a scientific understanding that is still evolving. The Walker lane is continuing to accumulate strain. The above, it is continuing to expand. And the interaction between those two trajectories is not static, which leaves the situation in a state that resists simple framing. It is not an immediate crisis in the absence of visible damage. It is not a negligible risk in the presence of clear geological evidence. It is a condition that sits between those extremes, where the most important changes are happening slowly, beneath perception, accumulating over time until they express themselves in moments that are brief, decisive, and difficult to anticipate. And somewhere within that slow accumulation, across mapped faults and unmapped ones, across years that appear quiet and years that do not, the system is moving toward its next release of energy. Beneath that evolving risk lies a quieter problem, one that is less visible than ground shaking but more persistent in its consequences. The Walker lane is not only under-recognized in public awareness, it is partially unresolved in the scientific sense. Entire fault strands remain insufficiently mapped, their histories untraced, their recurrence intervals undefined. The system's total strain is measurable, yet its distribution is not fully accounted for, leaving gaps between what is known at the regional scale and what can be predicted at the local level. Aftershocks help illuminate structure, but they do not reveal long-term behavior. And without that history, preparation becomes an exercise in approximation rather than precision. This creates a blind spot that is not a void, but an uncertainty layered over an active system. Communities expand, infrastructure accumulates, and the ground beneath them continues to adjust along pathways that are only partially understood. The April 13th event did not resolve that uncertainty. It exposed it, briefly, before attention moved elsewhere. And the system continues, distributing stress across faults that have names and faults that do not, moving toward outcomes that will only become clear after they happen, leaving the present suspended between what can be measured and what remains just beyond it.